go ahead and get started here. Thank you all for coming. Hopefully you aren't here for web spiders because the title might be a little misleading that way. Actually, it's an acronym for Synergistic and Perceptual Intrusion Detection with Reinforcement, which probably cleared everything up for you. Essentially, some research that I've been working on in distributed multi-agent intrusion detection / protection systems with response. Kind of a brief overview of the what we've been working on. Some of the goals we had in mind when we started out with this thing was to utilize new and existing sensors that are already on the network, firewalls, et cetera, that are already generating some data that can be analyzed. And this leads to needing to integrate a wide variety of heterogeneous agents into one system. And we'd like to also simulate a more human response, and preferably a line rate, obviously. The more human response, partly to make the system itself a little harder to detect, being not as crisp in its decision-making process, so you can't map it out quite as easily. And also to just have a more dynamic response system. And right now, we're pretty much focusing on that decision-making process, not so much on the gathering of the data at this point. So the actual development of the HID sensors, monitoring various data sources wasn't the key point of the research right now. Mostly we're trying to build a framework that could collaborate a wide variety of different inputs and deal with them accordingly. Part of the reason we were going with the heterogeneity is it's harder to fool. If you've got overlapping systems and overlapping detection regions, you can get a better coverage of the entire domain than just a single system could probably do on its own. And the old adage, many heads being better than one, particularly in this case where there's a diverse, very diverse computational models doing the analysis, and they're doing that analysis on a wide variety of different data sets as well. So you want different methodologies there to be combined. A little bit on the framework. The architecture at its basic high-level overview basically has a blackboard system in the middle with a number of different intrusion detection agents sitting out. They could be infrastructure devices that are already there, perhaps HIDs running on workstations or servers, maybe a network monitor sitting throughout different parts of the network, wherever is appropriate for a particular environment. And then we'd want to collaborate all those together, run them through that Blackboard manager, which will do the response, also do a lot of the reinforcement learning, which I'll talk about in a little bit. Then obviously an interface for the user, the administrator to control load balancing, how paranoid they want to be, for example. That was the big overview picture, but it's also an extensible hierarchical architecture. So that model that was on the previous slide could be extrapolated down to being essentially that whole model on a single HID, for example, collaborating different inputs on that system together, and then generating a result for that machine, which then is that agent for that machine and gets forwarded up to a more central one. Also, if it was a large enough network, this could be done just to compartmentalize things or provide redundancy, hooking up to different local blackboards, and then up to a centralized one eventually for management and readability. One thing we want to try to keep in mind is minimizing the network utilization as much as we could, low communication between the agents where possible. Pretty much they just respond with a response for a given event, and then the Blackboard can send back that reinforcement signal to update the agents and keep them dynamic. And then obviously there's some issues with communication security if you've got a distributed network. Again, this isn't one of the things we're particularly focusing on at the moment. Obviously you can try encrypting that data, set it up on a VPN or on a dedicated physical network. There's a variety of techniques out there. and the specific implementation is kind of up in the air at the moment. The detection agents themselves, as I've been saying, are distributed throughout the network, located wherever you have something that needs monitored, and they can be reading diverse data sets. So you've got one monitoring TCP/IP traffic, you got another one looking right down at a host at the process tables or syslogs or whatever is important in your environment. And then one of the big things that we're going to be talking about is the various soft computing methods that we're exploring to analyze this data. These different methods will be applying with very diverse responses, some of them more crisp yes-no answers up through fuzzy sets. And also it's adaptable, so by using incremental machine learning, they'll continue to update as they go along. The results from all these agents are then correlated together with a voting system, which helps ensure against a single, one machine suffers a Byzantine fault. It's not the end of the world. It will lower the voting score overall, but would still probably not drop the score significantly. And like I was saying, different computational models here. The yes-no crisp answers, simple probability, 80% that it was this particular type of attack, 20% a different type, or a little bit more abstract, a range, 60 to 80, that sort of thing. And fuzzy sets then being one more level of abstraction higher. Combining all of these, we're using something called mass assignment theory. I don't want to get into the math too much, but it essentially allows a mapping between the fuzzy sets to a probability distribution, and you can keep dropping down your layers of abstraction through that methodology. And it allows us to manage the consistencies between the probability distributions, the fuzzy sets, and all that sort of thing, so we can combine these really diverse data sets and responses into something more human readable and easy to look at, and you can print out and hand to your boss and say, hey, look what's going on. So just a kind of overview of this process. Each of these different agents could be returning different types there. They all get collated together. There's a big team voting system, and you get your final overall response. And then if you want to be able to do something with this data other than just go, oh, somebody's here, we need some sort of response system. And the level of reaction and response will be highly dependent upon the degree of confidence generated from those probabilities, and also on learning from what an administrator would have wanted that done there. So it'll analyze what you have been doing and try to imitate that as well as it can. This flexibility in the response rules, using some of these fuzzy logic rules, allows you to respond a little more fluidly to an event, and again, makes it a little bit harder to detect in that it's not such a crisp, it always does this when I do that type thing, so it makes it a little harder to probe. So the responses will be generated from all of the agents, collected, and a decision made based on what that final response probabilities are, and the response done, blocking that IP or just alerting an administrator or whatever is appropriate. Obviously, dependent upon the attack type, you want to do a different response for different attacks, and the detection confidence again. And these are configurable and with some sort of default for new abnormality type attacks. The algorithms will make a best guess or go off of a user-defined default. So some of the classification methods that we're exploring. Fuzzy logic, like I've been talking about a little bit. Decision trees, fairly straightforward there. Neural networks, self-organizing maps, and genetic algorithms, I'll talk about in a little bit more depth on next slides. All of these could be used for anomaly signature or classification type detection with varying degrees of success. Highlighted in blue the areas where I thought they'd be most appropriate, and a little bit of overview on some of their pros and cons. The decision trees make for a very fast analysis, but tend not to be very adaptable, whereas the self-organizing maps, on the other hand, don't have the greatest speed, but very, very adaptable to new and changing environments. And the genetic algorithms are variable in the speed since they're highly dependent upon the test cases that you need to run them through. So one of the decision trees that we're looking at is an ID3. Basically, it builds the decision tree that you make your final evaluation on based on the entropy or the information gained from any particular field in the data set. So in a simple example here where there's assessing somebody's credit rating essentially. If their income is high, we're just going to say that that's good, and if it's low, then we're going to say they're poor. So we're quickly branching off and reaching a conclusion after only analyzing one piece of data there. Then medium, we need to go down another level, see if they've got any debt, that sort of thing. So we, obviously a very simplified example, but allows you to reach a conclusion after looking at a minimal number of data points. This can be used as either a binary or n-ary classifier, so it could be used for anomaly detection or for detecting a particular type of attack. They're generally need a fairly good sample of the data in order to make a good decision. So collecting that data makes them a little slow to train perhaps, but once you've got it, they go pretty good, and they're really fast to execute. But there's no inherent support for updating themselves dynamically as they go along. Once you built your tree, it's kind of there, and it's hard to mess with too much. The self-organizing maps allowed you to build a decision map based on all your inputs, and essentially allows you to correlate these various inputs that are stored in essentially a large matrix, and then they, as new ones come in, they're matched with the closest one in the matrix, and then the ones around them are updated at a reduced amount, so that essentially the end result is that you get this clustering of similar types of inputs to similar regions of the network. And then the resulting map is highly dependent on both the initial configuration values that you feed it in, the learning rate, how much you update, as well as what the training values were that were sent in. And again, ideally, an n-ary classifier, each of these clusters being a different type or subtype perhaps, but could be used as binary. Moderately slow to train though, because you're going through that whole map and you need to slowly update and get things to converge, but very, very reinforceable. And another one that we're looking at a lot and hoping to use extensively at some of the higher level parts of the application are genetic algorithms. Simply, they're an evolutionary model to programming. Basically take, in this case, for example, we could be looking at configuration values, and then those would be the gene set essentially. You'd find ones that were good and basically breed them together to get a new agent and test that agent for fitness, and if it's good, then breed it and so forth. This sort of system's highly scalable. I've seen people do it for building FPGAs, right down at the bit code level to writing code, to swapping branches of trees around, to just doing those configuration values like I was talking about. So it's very useful for some of those initial configuration values, finding optimal states. One of the weaknesses, though, is depending upon how long it takes you to test out any particular child, it could be a very slow algorithm. And kind of the 2-minute description of fuzzy logic. Basically, instead of having simple, crisp numbers, 5.2, a lot of times when you make a measurement, you don't actually have that degree of precision. And it's about 5.2, give or take whatever degree of response we had. It also allows you to correlate linguistic responses. Strange has very little meaning normally to a machine, but you could use this to give strange a meaning within a fuzzy set. So it makes for a very intuitive human interface and makes the system act a little more human. It's a little harder to detect, like we were talking about earlier. Some weaknesses, primarily if you don't need to do it, then it's unnecessary overhead. So if you do have clearly separable or definable data, then it's maybe not necessary, but it does come in handy for a lot of stuff. I know one of the earlier speakers was talking about using it for fingerprinting and was getting some better results with that. So some of the detection methods, we're looking at sort of a 3-stage architecture. Signature detection, something like Snort already uses, useful for detecting things that are easily defined, particularly by regular expressions. And there's a lot of stuff out there that really works well for. And it provides quick filtering and uses regular if-then-else rules. So it allows you to quickly weed out things that are known bad and known good that are easily definable. The response is pretty much always a crisp decision. Yes, this was good. No, it wasn't. So what we're hoping to do is interface probably with existing systems. There's a lot of people who've already been working on this. They do it very well, so didn't see any reason to reinvent the wheel there. Some anomaly detection stuff that we're looking at. Pros hopefully can pick up zero-day attacks, or at least have a better shot at it than just a pure signature. If you've never seen it before, how are you going to have a signature for it? Also decent for picking up privilege abuse, some account hijacking, some strange behavior from the account. So it's got some good uses, but obviously there's the well-known drawbacks of it that you can essentially train it to accept malicious use slowly. But even there, it does provide a little bit of a buffer. Instead of being able to just jump in and do that immediately, you've got to take that extra step to train it. So it slows down the attacker a bit at least. And it can be a little more memory intensive than some of the other methodologies. So another advantage of it is it is nice for the linguistic terms interfacing nicely with an administrator or somebody who doesn't want to deal with raw numbers, which also makes it well suited for some of the fuzzy logic stuff we're doing. What we're looking at for our anomaly detector is kind of using a hybridization of that ID3 system that I was mentioning earlier in the self-organizing maps, basically using the ID3 to branch down the non-continuous data and then use the SOM to classify the continuous. Since those two methods are well suited for those two different ones, and it makes for a faster end result. We're also looking at something called a support vector machine that another gentleman I've been working with has been developing. They're good for performing binary separation. So you've got an n-dimensional array, essentially, and of data that you want to analyze and put into class 1 or class 2. And even if they're not linearly separable, there's kernel functions that you use with these that map them into a higher dimensional space so that they do become linearly separable and can do pretty quick binary classification of very large data sets. So we thought that would be an appropriate one to collaborate with for the anomaly detection. For event classification, it's useful for determining exactly what the attack type is, which you need to know if you're going to do a response. Also, it's good for knowing or for detecting semi-known patterns. So if you don't have a new variant of something comes out that's slightly different, It might get by a signature, but by using some of these systems here, if it's similar enough, it'll still pull up as at least having a probability of being that same attack type. And primarily, we're focusing on using the self-organizing maps for that since they're so adaptable, and returning currently probabilistic responses. We're also wanting, this is where we'd particularly like to use a wide variety of different agents looking at the data simultaneously. So ID3 trees, the support vector machines, and another method called the k-nearest neighbor, which is semi-related to the self-organizing maps, but a little less intensive. And hopefully by collaborating all of them together, we can increase the overall accuracy of the system and make it harder to get something by any individual one of them. So kind of a overview of the structure that we're looking at, filtering out quickly what is known to be good, known to be bad with the signature detection, and then passing it on to the anomaly and the classification systems and using those in parallel to determine a threat assessment, essentially, which we then perform an appropriate response on. Part of the reason for doing that multi-stage analysis, you don't need to do these more complex algorithms on the simpler, easier to classify events. If it's clearly allowed or clearly denied, there's no reason to spend more time on it than you need to. So quickly get it out of the way, and then if you're not sure, you can go ahead and do the more in-depth algorithms. Some of the reinforcement stuff, we want the system to continually update itself as it goes along. It's not a static environment out there, so we need it to continue to keep improving itself and learn from what's going on. So that's part of the reason we're exploring the various machine learning techniques and using the different models, because we don't want they all learn differently, and we want different impressions of stuff, essentially. Right now, the easiest way to do this, since not all of the methods support reinforcement learning inherently, is to wrap them all in essentially a weighted response system and generate that weight based on a trust level of that agent based on its accuracy of classification in the past. So as an agent provides a correct response, a lot of this is set up during the training, but then you can also do it by basing off of high scores from the other agents during runtime. You can then assign a reward or a penalty to that particular agent to kind of figure out which ones are doing a good job of detecting which particular attacks. So one particular agent may be good at seeing one type of attack, whereas it's no good at another, so you wouldn't trust its vote on one, but you would on the first one. If they're adaptive, when they receive their reinforcement reward or penalty, they'll go ahead and update themselves internally as well and notify the Blackboard team system, of their improvement, and then the team may choose to readjust that trust level or just wait until they've proven themselves in combat. So that same diagram again, just with an emphasis on the weights that are being applied to each agent, and those weights could then be further applied to a specific attack type and summed up into a normalized score. So anyway, the incremental part of it, the detection and response systems adapt to their changing environment. So as normal use changes, somebody does different things slowly in their job, or just network traffic changes over time, they'll be able to adapt. That's particularly important for the anomaly detection. And also for the classification, it's good for picking up new variants of known attacks or potentially entirely unknown attacks. Also, it's good for the response. If you start seeing the same sort of thing and your response isn't working, you may want to start updating that as well. Some things that we're looking at for optimization, again, right now this is largely a very simple prototype, so a lot of this hasn't been done yet, but one thing to improve the accuracy that we're looking at is if the combined result of all of these has a low confidence decision, then we probably don't have the right distribution of agents analyzing the data. Or if the anomalies are highly disproportionate to the classified attacks, then something isn't jiving there either. So easiest solution is to build a new sensor agent using some of those genetic algorithms I was talking about earlier. You can essentially find out which agents are most successful out of your group and build a new agent based on them that can then go ahead and start analyzing the data. If you start creating new agents, you don't want that to get out of control, so you're going to need to start trimming them as well. So if a particular agent drops below an allowable trust threshold, so essentially its input is no longer terribly useful, there's no reason to continue running it, so basically just trim it or call it out of the system. Also, if the overall system's using more processor time or resources than the administrator felt it was appropriate for their particular level of paranoia and other resources and things they wish to do, they can be trimmed in that case too. Instead of just getting rid of it entirely, you can also, with particularly the trees and some of the other methodologies, refactor the decision process and start trimming branches off those trees, simplify the process, and that sort of thing. You can collapse the self-organizing maps down, make them a smaller matrix that you're analyzing through, and really speed up the process that way. You can also start filtering out less relevant input fields so that only entries with higher entropies or information gain are analyzed. So, so far I've done just a little bit of testing, prototyping on this thing. Right now, we've pretty much been working on the classification system. The tests were pretty much designed to determine the effectiveness of multiple agents, whether or not that actually gave us a boost in accuracy, and whether or not going with the machine learning adaptability, they did prove to be adaptable, and whether or not any further effort was warranted in this direction before we went into too much more work in the other fields. So currently our classification implementation is using those self-organizing maps, which obviously I'm a big fan of. And they start out trained with a supervised data set. So the data that's initially passed into them is flagged as being a particular type of attack, just to get them started. The data set, we do have some live sensors that we're starting to get up and running, and part of the problem is we've got a lot of data, but it's not very well flagged. So we've been using a contest data set that came out for an IDS challenge a few years ago called KDD Cup. There's a link to the data set just to get an idea of what we're playing with. Right now, like I said, it's not everything isn't implemented, and it's very crude at the moment, but we wanted to see if there was an increase in accuracy with a number of agents, and we're fairly happy with going from a very low accuracy of almost useless at 76% to 97% by just adding a few more agents to the system. So that was somewhat encouraging. Also, we saw a huge decrease in the false normals, the false positives there, which one problem we have with that training set is it has very few actual normal events in it. It's largely attacks, so we actually have a little trouble learning them since there's hardly any in the data set. With a more realistic data set, we figure we'll probably get a little better result there. Also, one thing we were looking at is how accurate or how consistent the system was. So we're looking at the standard deviation of the accuracy over a wide number of tests, and it was starting to get fairly consistent the more agents we started tacking in, which was encouraging as well. Apparently had way too much caffeine because I got through this too fast. Basically, the conclusions we had from the quick little test was that we did see an increase in accuracy, both in a decrease in false attacks and false normals, as well as that increase in consistency. Naturally, adding more agents in, particularly with the somewhat kludgy code that's currently running this, there was an increase in time. There's a lot of optimization that can be done there at the moment, too. So that is the big question. Can this thing do anything at a reasonable rate? And I'm not sure, but so far it's looking promising, but we need to do some more testing. Some of the assumptions that I'm making to make it seem promising. Hopefully the majority of traffic can be filtered out by the signature system, in which case this wouldn't have to be analyzing every single event. I don't think it probably could do line rate doing every event. Also, the systems that are there can be significantly optimized. This code's been kind of cobbled together by some students trying to meet deadlines and so forth. So some of it, I think I was looking through it the other day and I saw a dreaded bubble sort in there at one point, so obviously some cleanup. One of the other optimizations is right now we're analyzing every single field of the data, and it would be good to filter that down to only the ones that were truly relevant for a particular type, which is part of why we wanted to use that ID3 SOM hybrid thing to get that sort of collaboration going on with the information gain and a reduced set. That should get us a significant increase in speed. So the brief overview, we did see an increased effectiveness of detection and classification. The data set did include some events that were designed to try to avoid detection by IDSs, and it had a better accuracy of detecting those than the more agents we put in, and when we converted it to a fuzzy logic probabilistic system, the accuracy went up greatly too, by about 10% on the 10 node one at least. Also, fuzzy response system, we hope to make it harder to detect or anticipate a response, so they can't hopefully fool your IDS into doing the denial of service on you by blocking a proxy or whatever. And hopefully it should be able to integrate with existing devices, since as far as the learning algorithms are concerned, they don't really care what they get fed as long as they keep getting fed the same type of data. So it's very extensible that way. As long as they get trained on something initially, they can continue analyzing it. Cons, obviously, you've got more agents, you've got more work going on, so it's going to take a little longer to process all these inputs. May require some dedicated systems for some of the blackboards. Network intrusion detection systems probably would be an appliance sitting out there, that sort of thing. Currently, we're implementing this. There's a collaborative network called VPNet in the Spokane area that's a 3 gigabit WAN between all the universities in the area, and we're going to sit there and try to analyze that. A lot of the traffic going over it is easily filterable, so we won't be having to deal with all of that simultaneously, or with the more advanced systems at least. And we'll see what sort of response that starts generating. We just started setting that up. And there's the website. I'm not a web designer, so pardon the site, and some contact information for people, which will be on the CD and so forth. And I guess I hope people have a lot of questions, or you can go chill for a while in the lobby there. Anybody? Yes?
What level of, in your genetic algorithm,
Yes.
what level of abstraction are the individual genes to the sensor or the group of, or
We're using them in a the question was, what's the level of abstraction for the genetic algorithm that we're using right now? Is it at the particular sensor or configuration values, or where is it at? And the answer is both, actually. Right now, it's currently implemented for the configuration values. We want to extend that to be for the sensors themselves, for the optimization of improving accuracy and efficiency too, starting to filter out the less accurate ones and create a new one from what systems we found worked well other places and build a new one off of that as an initial seed. Yes? Okay, so the question was, were we just doing the learning off of just the traffic that was coming by, or were we able to put in some user knowledge into it, essentially? And yes, largely the automated portions of it would be, currently actually, they're all live traffic. We do envision it going to more interaction with that user, the administrator saying, hey, these are this type of system. Actually, there was a gentleman before me who was talking about filtering based on what attacks worked for what systems. That sort of thing would be something that we'd want to look at including as well. So yes, right now the learning algorithms at the sensor level are just learning off of the data that they see coming in, but the reinforcement and response system that we have allows us to have another communication line coming in from an administrator to tailor that a little bit more. Anybody else? Yes? To leverage some open source options. Well, we would like to incorporate the responses from existing systems. So in that sense, yes. I'm not quite sure I know what you're getting at. Right. No, he was saying that there's a lot of non-trivial things that this isn't really dealing with at the moment, which, yes, that's true. Our focus was trying to do that classification and analysis of the data. The actual legwork of how that data gets in and where it's coming from wasn't the focus of this. Yes, there's a lot of people working on that, and I think some of them are doing a very fine job of it. And so, yes, we definitely want to piggyback on that work. We wanted to focus on trying to develop a little bit more dynamic and way of analyzing that data, though. Anybody else? Okay, well, thank you all very much. Sorry for cutting you short.